I have broken away from proposal preparation to bask in the warmth of actual science.
Okay, maybe we start a little earlier today, since some people will have to leave sooner. Caleb, do you offer to say a few words before we started? Yes? I don't know. Or do you want to wait? After?
Maybe I'll wait.
Okay, so Caleb will wait. So I have put together a few slides, well, more than a few slides, going through these papers kind of one after the other, because there seems to be a kind of a burst of interest in this topic in the last, well, year and a half, 2 years. I mean, not that there haven't been papers published in 2009, 2006, whatever, but it seems like there's a lot right now. Why that is particularly, I'm not sure, but I think it might have something to do with exoplanet studies increasing and the fact that we're going to start seeing a lot more, well, we hope anyway, Earth-sized planets from Kepler and missions like that. And I got started this because of a blog posting that Caleb posted a couple months ago, and I'm old friends with Kevin Zonley, who's the co-author on one of the main papers in this series. So I think we all know that the issue really is that we know the sun was 20 to 30% less luminous than today in its early history, and the question is, how did the Earth maintain a warm climate back in that time? And we know we have a pretty good evidence that the Earth's climate was warmer back in the Archean. And I printed out a few things from these from Wikipedia for those of us that cannot keep, as I've said before, the Proterozoic straight from the Paleozoic, although we'll never talk about those today, but it tells you when the Hadean is and the Archean. We're going to mostly talk about the Archean period for those that don't know their geology very
As a
well.
physicist, can you give us 2 sentences on reminding us exactly why why more hydrogen? We're not burning helium now, but it's, I forget. I learned it and I forget.
Yeah,
It's moving out. It's the central temperature.
There's a simple intuitive.
Well, this may not be an entire academic level I try to give it to my students. When you have more helium, as you have more helium in the core, the helium is the heavy stuff. The core is denser. It compresses the core more. And the fusion reaction, because it's like by quantum tunneling, a little compression goes a long way in getting more likely that the thing can get across. And so there's a huge, there's a very strong compression effect. And so
that's
so
compression, and then
helium
physics or then complications.
Pulls the core close together, makes the hydrogen burn faster. And so the sun is still getting brighter. Am I not correct?
Yes, absolutely. Okay.
So one question is, sorry, why don't we know that number at the percent precision?
Yeah, 20 to 30.
Because we mine it.
Well, I say 20 to 30 because recent papers have said, some papers say 20, some papers say 30. I don't know. Do you know exactly why they make such a big range?
Well, wait, isn't the Archean a few billion years or something?
Yeah.
Yeah,
Well, over that billion years, it
Well,
probably changed by 10%.
Maybe during the Archean, yeah. But I don't think it, well, I've never seen the numbers exactly how it changes over time, but I wouldn't imagine that it's 10%, but I don't know. So I didn't
Well,
write
it
it.
was 30% 4.5 billion years ago, and then 3 billion years ago, it was 20%.
I mean, it need not be linear, but he does have a point. I mean, the things have not, the sun hasn't undergone a phase change, so to speak, between when the Earth started and now. So if there's been a change of that much, since in the last 2 billion years, there must have been a significant change.
Linda has the exact numbers.
This is Gus model. And so if we assume almost 30% right at the beginning of Earth's history, then by the time you get to the end of the Archean around 2,500 million years ago, you're up to
82.
82.
Okay, so that's a range over the Archean.
So thank you. Yeah, because some papers are actually assuming 30 and some are assuming 20, and they don't explain why.
Part of it can depend on solar modeling, though, right? Which depends on heat transport within the sun, which depends on turbulence and things like that. I mean, I don't think this is a really.
I think all the models agree pretty well.
People tend to just use this GOF model, which is one single parametric fit to all of those things, and so, you know.
So the astronomers believe they know that number at that level of
Pretty accurately.
precision.
Yeah, I talked to Vittorio.
For a
Cornuccio.
standard solar model, the question is, can you change things?
Right.
With it? Yeah.
I talked to Vittorio last week about it. He said he thought the number was very solid. Actually, he didn't think he was going. That these models are very good, is what Vittorio was.
I think I recently came across a paper, I stumbled across this a few months ago, where they actually claimed that, you know, with small variations to the standard model, you could actually get a far less reduction, and so maybe there was no faint young sun after all.
Well, one story that I know, there was a paper maybe a few years ago. People said maybe if the solar wind, our idea of how much mass the sun lost. If you make that more significant, then maybe it can help. But that's not considered a consensus view. So I think the standard story is that that's a real number you have to deal with.
Yeah, because the solar mass loss, so one way out is to say that the sun is 10% less massive now than it was back then. Okay, and that loss comes from just normal solar wind and so on, which is extremely difficult to pin down because making those observations of comparable stars is extremely, if not impossible. So the best limits I've seen, the sort of the high end of the possible mass loss is no more than 3%. But you also, if you had that much mass loss, you'd run into dynamical issues with the planetary system itself. So,
which actually leads me to my question, if you don't mind me changing a little bit the topic. What about that other term in the inverse square law? How certain are we sure that that hasn't changed? No, the distance.
Distance.
oh, I see.
Migration.
Oh, migration of the planets. Okay, let's move on. Okay, so this is a little kind of
Touchy
quick
subject.
summary I put together, but we'll go into more details in a minute.
Actually, it would
But
go
It would go
right
in the other
direction.
direction, most likely, yeah.
Well, it would go with mass loss from the sun would push the orbits out, right?
So we were closer to the
Wouldn't
sun,
it-
so
Yeah.
we're better off by a few percent.
But it was also that much hotter, so actually then you turn the problem around and it would be too hot. So-
okay, anyway, so let's assume the sun was somewhere between 70 and 80% as luminous as today. Some of the first theories that maybe there was more CO2 or CH4 methane present. We'll talk a little bit about that. At least from reading these papers, and I'm not an expert in this field at all, and neither are most of the authors, apparently, there's a lot of evidence that CO2 concentrations were not much higher back then than they are today.
Well, can I just ask a question about that? If like anyone knows the answer here, because the atmospheres of Mars and Venus are both similar. They're mostly carbon dioxide with like 4 or 5% nitrogen.
Yeah.
Why is it now believed, because one time it was believed the early atmosphere of the Earth was similar, why is it now believed that before life, most of the carbon dioxide either had been taken out of the Earth's atmosphere or the Earth didn't produce carbon dioxide? Why is it believed that the Earth's pre-life atmosphere was so different in composition from Mars and Venus?
Hydrological cycle, isn't it? And weathering. I thought it.
Yeah, that's part of it, I think. Yeah, the CO2 cycle on Earth.
I mean, we have an ocean, we have a lot of water.
Okay, so
You
the
have calcium
ocean
all
was
over the
simply
place.
responsible for taking this out before there was any life. Well, before life was always was almost always different. Before life was significant, the ocean simply took it all out.
But is there an issue? I mean, was plate tectonics more active and therefore dredged up more carbon dioxide in the past?
No idea.
Yeah.
But
We
that
also-
works the other way anyways. We're trying to get rid of the carbon dioxide.
Yeah.
But wait, I thought this long-term negative feedback of the carbon loop was a weathering.
Well, that's the thing, and you don't know what continental mass you had.
Yeah.
Yeah.
3 billion
Which will-
years ago.
And it also depends on what kind of crust you're weathering.
So since CO2 would not work, apparently one of the first mechanisms proposed was from 1972 by Sagan and Mullen, and they proposed higher ammonia concentrations. But that was found to be problematic almost immediately because without a UV shield, it disassociates very quickly, and you suddenly have a nice nitrogen atmosphere and no ammonia left. So this was not a solution. Bill Rossow, actually in '82, even probably the first proposed cloud feedback solution to this faint young sun paradox. It's a very short paper. I didn't list it for people to read per se, but it just goes through some back of the envelope calculations. He has one nice little little plot here. So let's look at some of these papers. So the first one I'm going to talk about, or I think we can discuss, is this 2010 Rondinelli and Linzen. Linzen's a famous guy for many people, at least in this building, I think. I'm not sure outside of this building. And their idea is that thin cirrus clouds in the tropics, that has to be specified, provide a solution to this problem. So basically the idea, I think, is that these thin cirrus clouds have a higher IR heating effect because they're very high, than shortwave cooling, of course, and therefore a strong positive cloud radiative effect. And they claim that Radiant's recent satellite estimates confirm this. Well, anyway.
They're not reading any of the literature, evidently.
Yes. Well, they get criticized by many others. And by the way, Dr. Ackerman here is one of our cloud experts, along with
Thin
Tony.
cirrus have a positive
Thin cirrus.
cloud. Yeah, thin cirrus do.
But I mean,
Just have to decide what your
ultimately, they
definition
seem to
is.
be saying it's their iris hypothesis.
Oh yeah, I know.
Yes.
I know. Yeah.
Anyone who wasn't
where
his
they go, where
postdoc
they're going
comes
from
up-
effect to feedback. Yes.
right. No, you're right.
Yeah.
You're right.
Okay. So they do talk about just increasing CO2 and CH4, and I've already said this, that CO2 probably could not have been more than 10 times the present amount. That's from weathering, from looking at siderite versus magnetite, I think. I forget the exact rocks, but they quote several lines of evidence, and so do several of the other papers. Methane, they say, is possible, but not when the ratio is higher than about 1, because you have formation of this reflective organic haze, which causes a lot of problems, which we're going to talk about a little bit later in this paper by Wolf and Toon, where they find a way to make the haze actually work to their benefit, not against their benefit. Okay, here is one of the plots from that paper. Here's a one-column simulation, fraction of tropical coverage on your left. This is the luminosity of the sun. Here we are today, around 300K. And let's see, that's the black dot. White dot is up here. That's with the solar luminosity about 75% of present, and a fractional coverage of these cirrus clouds of 0.55. You can see you're still quite chilly, and the gray dot is with a much lower fractional coverage, more or less what we have today with the same luminosity. You can see would be below freezing. So you have to have some kind of feedback in this model. That's the 1D or one column tropics. Here they play around with different CO2 concentrations for 80% solar luminosity. The current is the gray dashed line. This plot didn't come out very well, but there's a gray. This is supposed to be gray. Apparently our projector's not very friendly. The green dots is the paradox, so that's this green dot down here for S equals 0.8 with the fractional coverage we have today. That doesn't work out very well for one present atmospheric level of CO2. And they say you need at least 20 times present levels of CO2 to get up to 273. So basically up here is what they're saying. You need at least 20 times, according to them. So it's hard to solve with only one, with the current amount of CO2, as they're trying to prove here. You really need complete fractional coverage of 1 to manage that. So you have to get, again, fractional coverage all the way on, which kind of fits their model, right? This is their model output, showing that with complete coverage you get just above freezing. This is not as warm as what we have today, of course, and that will present problems that the other papers will point out. Okay, so they checked several other things. Sensitivity, cloud, water content. The clouds have to be just right, not too thin and not too thick. And there's several figures that go along with this. I didn't think I'd go through all of them. Sensitivity to fixed height, assumption height of the clouds, water vapor feedback, and meridional heat flux. They claim that most of these are minor effects and that the prescription works with these thin cirrus clouds at high altitudes with this moderate CO2 concentration. So they find a way to make these thin cirrus clouds work to get above freezing, but just above freezing, as you saw in those earlier plots.
Or is that
Yeah, it's, well, in the paper they say over the tropics. I mean, mostly over the tropics. That's where all this stuff happens. So, but it's not clear. In the paper, then they're a little ambiguous at times. I can't tell if they mean over the entire planet or over the tropics with the fractional coverage stuff, because they make a big emphasis about it being tropical, but then they use this in
So
a
this is
sloppy
a
way.
one-dimensional.
Yeah, this is one column model.
So actually, maybe you came across this when you were looking through the papers. One thing I didn't see in any of the literature was discussion about what the Earth's rotation rate was 3 billion years ago.
Was it faster?
It should be.
Oh, yeah.
Well,
How much
it should have been. It could have been 12 hours.
It was definitely.
Factor of 2?
So
Could have been
what does that do to heat transport equator to poles?
So that makes 1D model less valid, I think.
Right, and presumably it reduces the
Reduces heat
transport.
Right, so it makes 1D model less valid.
Right.
Anyway, I just
Also,
That's a good
tropics-
point.
whether that's
That's a
Yeah,
good
the tropics are a lot narrower.
Yeah. Well, Goldblatt and Zonley bring that up towards the end of the paper when they explore this big parameter space, but they say, well, first we do this to try to figure out what parameters we might want to use, and then we go back and try to do a 3D model, but that's a lot more expensive and takes a lot more time.
So
than just
I
doing a
didn't
bunch.
look at this one at all. So what is their mechanism? Why is the tropics covered with thin,
They
high cirrus?
don't really give a mechanism. They just say that there are clouds, these high cirrus clouds are there, and
But I think it's what you
And it's
alluded to
too.
earlier, Andy.
But I thought the iris was a solution to the warming sea surface. This is a much colder sea surface, and so it works where whichever way you go from here, you get more cirrus.
No, see, because they're, right, the iris
Oh, it's
says
to
that
get
as
less,
you go
to
to a
get
warmer,
less.
they
You're
say
right,
that
right,
when
right.
you go
So
to
you
that
go the other
day,
direction.
Linson says when
Go
you
the
go to
other
a warmer
direction.
climate, you get less cirrus, which
Right.
there's no actual
Right.
evidence for in the observations. So therefore, the opposite of that, I think, would be.
Yeah, sorry, so it is all based on this iris hypothesis, which, am I wrong that they're the only people that really believe this? Is there a strong?
They're just about the only people.
They're
I
just
think his
about-
postdocs agree.
The people dependent upon jobs agree with this guy, okay. All right, so it goes back to this iris hypothesis of Linson.
But the 1D model that they're using, I mean, do they just make an assumption about the clouds and then stick it in there? Or
Yeah.
are they, so they're not actually internally calculating something?
I don't think so. I didn't get that impression.
I mean, that is an issue, like how you get that much water up in a really cold planet.
Yeah.
Right, that's, right.
Well, this paper gets criticized by many others as we go on here, as you'll see. Okay, so this paper from April 2010, just a year ago, by Rosing et al. Andy said that one of the co-authors is a more famous person, but I don't know any of these people. Sleep, right? Norman
Yeah,
Sleep.
Norman
Norman
Sleep,
Sleep,
yeah.
Okay, so you guys know who this is. So their title is No Climate Paradox Under the Faint Early Sun. And they basically say that there was a lower albedo Earth because of less continental area and lack of biologically induced cloud condensation nuclei, which we'll go into a little bit. They present lots of evidence again for low CO2 concentrations.
When you say low, you mean like 3 times present or
Yeah,
something, right?
around the present amounts, up to a couple times what we have today. They claim clouds over early Earth are very different. Again, these cloud concentration nuclei were lower. They believe the drop size was bigger. They have a non-oxygenic atmosphere, and the biosphere is devoid of plants and algae, or less anyway. So you don't have the biochemical ability to create drops the same way you do today. Sulfur also plays a role in that. And they give some evidence for that, where drops basically are bigger over oceans than they are over land, which I didn't know before I read this paper. And more transparent, and the atmosphere would be more transparent, so lower albedo ocean means strongly expressed fraction of total planetary albedo. So again, you have more ocean coverage, you have a lower albedo, more absorption, warmer planet, essentially, is what they say.
But they claim that can offset the 20 to 30%. It sounds like a big effect.
Yes. Yes. So this is the.
So this is what current to future climate people are calling the cloud indirect effect.
Oh, are they?
Which
Okay.
in the IPCC reports is generally listed as the largest error bar in projection. it's certainly thought to be negative. Right. The question is, how much of it, how negative is it?
Right. I think this is the key plot from that paper, where he shows continental fraction of our surface above is a fraction of time. So this is time gigabyte before present. This goes from 4 to 1. Surface albedo changes, rough albedo for droplet sizes of for the full planetary albedo for droplet size 30 micron, which is bigger than any droplet size I think we've measured today. Is that right, cloud people? We don't measure droplet size bigger than what, 20?
Well, for
Or
stuff
more.
that stays in
Yeah,
clouds,
that's-
Yeah.
stuff that's 30 microns is starting to drizzle out.
Right. Okay, so 30 microns, 900 parts per million volume CO2 and CH4, quite a lot, I guess. And then this is the key part here. So this is surface temperature. The blue is 375, so they use less parts per million CO2 and 1.7 CH4.
Do
This
they
is
mean
with
900 ppm?
they call it
CH4?
ppmv,
P-
parts per million
now it's
by unit
2.
volume, I
We've
guess.
got that. It's 2 now. 2
Yeah, yeah.
ppm. Yeah.
Yeah, yeah. Anyway, that's what I'm just quoting what.
Yeah, I'm
they
just
put in.
that's what they said.
Yeah.
Okay.
So the blue is for 20 micron droplets. I think what's interesting is about how the droplet size makes a huge difference. And in here we have 12 micron droplets, more or less what we have today. So the droplet size makes a big difference in the temperature in their calculations. The green is with more concentrations along this level with lots of CO2 and CH4. Again, here the droplet size doesn't matter so much, as you can see in this particular scenario.
And all of this accounts for the change in luminosity.
Yes. So here's the luminosity is changing, and then the planet is getting warmer over that same period of time.
We have 1.7 CH4 today, right?
This is 2,000 times. The methane is 2,000 times higher today. Are you sure it's not
Can we
ppb?
see it?
Yeah, you can just double check.
Just
it.
checking because it's really.
Yeah.
I mean, the CO2 is about 3 times today, and the
Well,
methane
they-
is about 2,000 times today.
I thought that they say that CH4 has to be lower back then. I forget the exact reason. But I see what it says.
No, you're
Am I off?
1.7 parts per million.
Yeah.
Now.
That's what I said.
Now, and 900. Oh, so, yep, 900.
So I was right. I can copy correctly.
That seems a bit extreme.
Wasn't questioning you, just them.
Yes. That's what they
So now we'll question them.
Good. recommend SD.
The gray areas or whatever,
Yeah,
are they
use methane.
uncertainty?
Yeah, I think
Because the
that's
continental
these.
fraction thing, how does that?
That's just lots
That's
of
just
hand
up in the
waving
air.
for a significant amount of time
Yes, you will.
on that diagram.
But that's a potential solution.
There's a lot of, you can see there's a lot of
Yes.
room for uncertainty here.
But for
If you're unsure of your conclusions, put large error bars. Okay, now we can all go home.
Find virtual evidence that-
wrong.
Well, maybe not quite.
Surface albedo. What's surface albedo now?
Sorry, what did you say?
The
Max?
range of the
Oh, maybe it's because they stopped before 0.
the range of the planetary albedo in channel C seems to be less than the difference with today. If take today
We were
as
just
a
discussing that. They don't
reference.
quite get to 0, because come on, today we know what it is. That's got to be
But
the answer.
what would have changed, I mean, the range, the time range there is smaller than the difference with today, so what changed so dramatically to give such a large albedo today relative to what those?
Snow.
Yeah.
Uncovered land and
like
snow.
glaciation?
Yeah, I don't know.
Well,
I don't
especially
know.
because like around 500 years ago, actually maybe 400 or something, but that was the Devonian. That's when you started getting land plants, which were darkening the continental surface. So that would.
No, they only darken the visible. In the near infrared, they're bright.
Mm.
You can actually get higher albedo than maximum.
So does the planetary albedo go up then? I mean,
It can go up, plant, looks darker.
But I mean,
Who's on
most
most
of
of
the
the
radiation is in the visible.
yeah, right.
It's about half. It's about 55% in the visible, 45
But
in the
are you calculating albedo across the whole shortwave?
Yeah, I'm sure that's what they're talking
Yeah, so
about.
then if you
They're
go
pretty
to-
close. They're not.
You go to near infrared.
So actually adding plants doesn't really change the amount of energy captured by the planet for a given amount of insulation. So that's the upshot. Like the changes in the UV are offset by changes in the IR, right?
Well, it could actually reflect. It could actually reflect more. So.
Well, one of the papers they talk about the rise of plants and that actually makes the land more like
Cool.
similar
That's
to
why-
the
that's why
ocean's
plant
albedo
canopies
actually
are cool.
over time.
Yeah.
But you're saying that's not the case
No.
in the IR.
It depends
Yeah,
also
IR.
what you had before. If you have desert everywhere, then it's a higher albedo. If you have just I don't know.
Well, but most deserts are not sandy, bright deserts. So a lot of deserts are really sorry.
Go.
Old time stuff.
Yeah.
Yeah, so surface albedos for non-vegetated places, most of which are, not the same, they can be 15, 17%. And plants and forests can be similar over visible to
So you only changed the near-infrared, so you're actually higher in the albedo.
Yeah, but I mean but deserts are bright sand deserts are actually pretty anomalous.
Yeah.
Well, doesn't the fact that this is inverted from this tell us that this is all about the fraction of land and to ocean? No?
It's definitely, they think it's a big component.
But the key aspect
Do you
here is
think there's
actually
more
changing
land?
the continental fraction.
Yeah, that's the big component, changing
Right.
continental
And
People
fraction.
had not
there's-
proposed that before.
No.
If there's more land, you think it's a darker surface.
Yeah, it's a dark.
So that's probably all that is.
Yeah, that's right. They don't invoke any clouds. This is all based on greenhouse gases and continental fraction. This paper. So their models.
They have really big droplets that are forming now.
Yeah.
And then the ocean productivity causing clouds. I mean, there's a lot of ocean productivity underneath stratocumulus decks, but I'm not sure anyone would believe that the ocean productivity is generating the stratocumulus decks.
No,
They
but
just happen
you
to
could
be-
say nowadays we don't care about the critters so much. And it used to be before we were causing such trouble. Maybe that was. I mean, no one has come up with any evidence to say Charleston or all were right or wrong. It's other than to say it's very, very complicated. We just don't know. That's my impression.
We'll get more on the cloud stuff later on. Okay, so then April 2020 2010 casting. He gets into this. He recaps the evidence in Rosing. He notices one problem: ice albedo feedback is ignored. He says in their model. Ice caps will probably start to grow with these low surface temperatures. Their temperatures are not that high, and he claims that'll fairly destabilize
So that's
the
early
climate.
on.
What's that?
Early on, there is low temperature.
Yeah. These
So
models do
it-
not
it-
give you super high temperatures. And he claims you need 3D models to prove the hypothesis, as Caleb was pointing out earlier, not just these simple 1D. He likes the idea of these reduced greenhouse gases because, he says, as the O2 concentrations rise, the other gases will decrease, and claims to rapidly trigger glaciation at the end of Archean. And that piece of paper I showed you, they call snowball Earth, happening just a few million years, I guess tens of millions of years after the end of the Archean. And he says that fits in very nicely with this picture.
I mean, it doesn't even have to be sheet ice, right? I mean, just precipitation, snow, and then you got to start worrying about droplets and things, right? So.
Well, I don't know how much how much glaciation he's talking about, but well, Andy was saying that I guess many people don't believe the snowball Earth.
No, I think
actually took
slush
place.
ball. Everyone's willing to go along with a slush ball. I think.
Depends which one you're talking about. This one is probably closer to the iconic, everything almost totally frozen over. Because
This
given,
is not
given
the
the time period.
Proterozoic one. What is it?
This is Paleoproterozoic.
Uh-huh.
So this is over 2 billion years ago. The slush ball is Neoproterozoic, and that's between
Neoproterozoic.
720 and 630 million years ago.
So people are liking
Well,
real snowball.
people don't have as many complaints about a real snowball back in this
cap
time.
carbonates or something like that.
Yeah, there are things that look a little bit like cap carbonates, but it's not been under the same focus as the younger intervals, and so there just hasn't. If people are disagreeing with this, it just hasn't come out in the community.
Okay. Then we move on to Wolf and Toon. And this is this fractal organic haze business, which we touched on in the first paper. They think that this fractal organic, aggregate haze was found, they find that it's optically thick in their simulations in the UV, while transparent at mid-divisible wavelengths. And we want UV for a very specific reason. So in the Archean atmosphere, we know it was mostly consisting of these things. We know dense CO2 is impossible again. We go back and from that very early paper with Sagan et al., they decided that if you have CO2 plus CH4 and a certain amount of ammonia, you can get the greenhouse effect to work quite well. But the problem was, as I said earlier, was that past studies found that this ammonia would disassociate because of the UV radiation. There's not much UV shield into N2, and that plus the CH4 would create a haze, which would offset any greenhouse warming from the former greenhouse gases.
How does that haze happen?
The haze, yeah.
How does that haze happen?
How does it happen?
Yeah.
It just combines. This gets disassociated into N2, molecular nitrogen, and that combines with a methane to create some kind of haze, they call it, which we actually see in, I think, the atmosphere of Titan.
Well, I was going to ask that. So are they invoking something that has similar properties? I mean, like,
Yes.
so for example, the Titan haze is not transparent, invisible.
Right.
So there's something different about the haze that they're making that.
Well, they say that it's the same haze, but probably the thickness is different. I don't know. They claim it's optically thin in the visible. I don't know how thick the haze is, again, with little cooling effect, and then optically thick in the UV.
Yeah, I mean, my impression with this paper was that they run some kind of simulation to ask what these fractal aggregates would do, but it's kind of, I'm not sure there's real evidence that you build fractal aggregates like that. It's more that if you did, you would have.
Well,
this
but
effect.
but they do say that they think it does match the properties of the
But I think-
fractal properties on Titan, right? Because they say first the studies were they termed sphericity before, and then they claim later on that it produces the scattering properties
Okay,
of Titan's
so-
haze.
right, then I
So
just-
these
the
fractal
question
aggregates.
is, what is it about in this parameter setting that gives them something that's optically thinner than what's on Titan? Because certainly the one on Titan's not optically thin.
But again, it depends on how thick the haze is. I guess the haze on Titan's much thicker. I mean,
Right.
physically thicker.
Right, so this, I'm
how,
saying back,
how
so what's
optically
different
thin
about
is
this
it?
parameter
Yeah.
setting that gives them a thinner rather than a comparable to Titan or a thicker
Yeah,
Titan?
yeah. I don't think they go into that. This is not a very long paper, so I don't think they go into those details.
I mean, lots more UV
Yeah, we have more
here
UV.
than
Titan.
absorbing the haze on Titan.
Yeah, absolutely. But I mean, the idea here is to protect the ammonia, right? So they want a UV shield, and this works quite nicely for that. If you don't have that UV shield, all of the ammonia will convert into molecular nitrogen, and they say in less than 10 years.
There's no chemical mechanism to remove chemistry reaction.
They don't talk about that, they just talk about the UV flux, basically. But it assumes all the ammonium is below this hazy shield. That's one of the criticisms of this. So if the shield is too low, it doesn't help you. It's got to be quite high, and it's not clear where the shield, if it existed, where it actually was. In essence. But I think it's a cute idea.
But again, now just going back to Titan, which is sort of the only actual data point we have.
Yeah.
About these types of things, right? I mean, that haze is way high up.
It is way high up, so it could
Hundreds
act.
of kilometers up. So,
Yeah, but so I don't know what they mean by this. It produces scattering. They didn't go into much detail. They just say this basically, that it produces the scattering properties.
Yeah.
So, but you're saying that this.
but I'm saying that the altitude doesn't seem to be that much of an issue if
Okay.
if you go by analogy to Titan, where the haze is at
Uh-huh.
very high altitude.
Okay, so maybe they just didn't
Because-
address it in this paper, and the other paper said, well, you didn't address this, but
Yeah.
they probably said, they know like you, Tony. Oh, it's high up, so you don't.
Oh, I'm sure they do.
Yeah.
It certainly is.
Yeah, but the other authors maybe don't know.
Yeah, I don't know who it is.
Yeah.
I think a graduate student with Brian.
Do you think the Titan data gave them the idea for this?
Yeah, it sounds like it, right? I mean, because Brian Toon, I think, wrote a number of papers on it. I know wrote a number of papers on Titan back in the 1980s and 90s, and so hard for me to believe that he's not thinking of Titan.
Okay. Then Chiba chimes in just a little bit later. This is a little letter about that previous paper, going through the history and mentioning that Sagan paper and how these other guys later said that that wasn't possible, the ammonia. Again, I think we've covered most of this, but he says that the thicker CO2 solution is still possible, but given what I read in the Rondinelli-Lindzen paper, I don't know how that is given the geological evidence, so I don't know why Chiba says that. but again, he says this again, he likes this fractal haze, but problems making it sure it absorbs all of the UV before hitting the ammonia. But again, maybe Chiba doesn't realize this stuff is, if it exists, it's super high up, and but it's surprising he wouldn't know that.
Yeah, I think he would know that too.
Yeah. So,
So
why?
there's something about the parameter setting for this problem
That's we don't know
that's
about.
presumably that we don't know about. That's giving it difference.
Then maybe Chiba knows something. Okay.
I think they just assert that it's up there, and like, we'll prove that it wasn't.
Yeah, this is the This is just a plot from Chiba's paper showing the surface temperature with the ammonia, plus you can see what a huge effect it has.
Wait, here's their sentence, which you underline.
Yeah.
The calculation assumes that all ammonia lies beneath the UV shield.
Yeah.
That's it.
Right. Yeah, that's all they say. I know.
That's their justification.
Yeah. Well, that's their statement. There's no justification.
We said so.
Who's reviewing this?
Yeah. Well.
And is that, I mean, is it a photochemical model that they're doing, or are they?
They do some
actually create-
rates. They do some rates of reduction in source, but and such. But no, I think it's really just optical calculation.
Yeah, I guess the question I give you assume that there's some kind of surface source of ammonia and methane that's then diffusing upward. Then, and if you actually have chemistry in this model, then does the UV get the methane first to make the haze before the ammonia gets high enough to be destroyed? Right? Or are they not doing anything that's
I didn't read anything like that.
It's just an aerosol model,
Yeah.
and
So it's not chemistry.
it's in a three-dimensional model, global model, but it's just an aerosol model.
They specialize in this sort of chemistry, though. Brian does
Right,
too,
right,
in ammonia
right.
chemistry.
This
and
is
so
not a
on, so-
chemistry model. I mean, they don't say that, and it's not.
But anyway, if you can get ammonia to last,
Oh, I see.
look what it does for you. It solves the problem in essence, right? If you can get it to hang around that long. I don't know if you can. Maybe they don't know if you can. But okay, so that's the Chiba. Then there was this little there was two little letters written in about these papers. One of them was very critical. She must have been a biologist or something. She says it's all rubbish. Basically, I forget what's her name. This is this the one? Yeah, no, I'm sorry, this guy, Michael John Russell, he writes this. He doesn't go for the haze, and he says there's a lot of evidence that this is rubbish, basically because of biochemistry, drawing on C2 and H2 as the main nutrients of life, and some other arguments for that. So they're very dismissive, and Russell tries to reply to that, but
Why is that an argument saying if you have enough ammonia atmosphere, you can't have CO2 and hydrogen?
well, he says, okay, I can just read you the first thing. Wolf and Toon based their fractal haze theory on the assumption that the Archean atmosphere was primarily molecular nitrogen. Their report includes no references for this prevailing view, and much evidence can be amassed against it. And then he says, geologists since Darwin, he's Darwin, look out, have uniformly argued for a CO2 dominant atmosphere for the early Earth. Period. Then some other stuff, but basically that's the argument. Like, okay, I mean, Darwin.
Which Darwin?
The operating system. Anyway. So,
Their last sentence, by the way, is someone should do this with a model that
Yes.
does chemistry.
Yes. Absolutely. They always put at the end like what should be done. They don't do it themselves. Okay, and then finally the paper that kind of sparked all this is this Goldblatt and Zonley. I read all these actually reverse. I read this paper first, so my comments are kind of messed up. But in essence, they use this kind of, it's again a one-column model, 3 layered randomly overlapping clouds to try to get the energy budget to work out while being consistent with observed cloud climatologies today. So remember, other people are invoking other kinds of cloud climatologies to justify bigger drops and all this kind of stuff. They say, we're not going to engage in that. We're going to just try to get away with using different normal clouds, but overlapping in our model, essentially.
You know those are GISS's, that's GISS's cloud
Is it?
product.
Oh, it is. Okay. I didn't know that. They claim that decreasing just the surface albedo of the Earth, which we saw in those earlier papers with the continental, contributes no more than forcing a +5 watts. So they say there's no way you can do this just by changing the surface albedo of the Earth, regardless of what these other people say. They don't argue they don't give a lot of arguments for it, but that's what
Well,
they
actually,
say.
Ron and I were both at a seminar TC, which he was sort of making the same case for today's climate, that basically surface albedo is actually just not that big a deal because clouds get in the way of everything. Clouds are what are actually controlling the planetary albedo. So I mean, I think it's consistent with that view.
Very good. All right.
It's interesting to say that because you told me to read one section, they don't get the surface albedo right. But I guess if it is important, you have to get
It doesn't matter if they get it right. Yeah, I just a statement for those of us that are not in this field. Cloud absorption, I thought this statement was important, is largely independent of wavelength in contrast to gaseous absorbers, which I think those of us that don't work in clouds don't think about that so much. At least I had never really considered it. Makes sense, but I thought about it so much.
in the visible.
Yeah,
not in the near infrared.
No. I should have put visible there. Sorry, Andrew. So they go through the papers and they criticize them. They say that the thin cirrus in this paper has twice the water path of their normal stuff. Their thin cirrus has to have thicker clouds, whole sky coverage, and they have to raise the height of the clouds quite high to get the forcing just right, is what they say. So just summarizing the problems with that. And they don't think that stuff makes this that model very realistic. Those very high thin cirrus, or I guess he says they're a little thicker than they claim. Again, that rosing decreasing the low cloud albedo using these very large particles. They decrease the liquid water path. They say that's arbitrary. I don't know enough about that. Maybe the cloud people can comment on liquid water path in clouds and what that.
Nobody knows. There's no justification.
Okay, nobody knows. And they say simply there's not enough forcing available for that model. And they talk about that in Figure 12 of their paper. Go.
So 50 watts is their target. So
Yeah.
it's a very nice thing. You need 50 watts. Yes. And so they say basically you can do all you want with low clouds, but how about we get rid of the low clouds, and that gives them something like 25 watts. So it's like you can't do anything with them if anyone gets to halfway there.
Right.
In fact, that's all they had to say, but they wanted to rub it in.
Remember, Kevin's going to listen to this tape later. Okay. Again, these are just my little summary comments. So they assess changes to the radiative properties of the clouds with respect to that faint young sun paradox. Again, a single global mean atmospheric column with a range of cloud properties. Try to match the Earth's energy budget, and they compare that to a cloud-free situation. Again, they change a whole bunch of things: fractionation, thickness, height, particle size, and try to explore really huge phase space, parameter space. Water vapor windows permitting significant surface radiation to escape, but the clouds and greenhouse gas keep that in. So you can have water vapor that's fine, but the clouds save you, I guess, from that stuff escaping through those water vapor windows. And the cloud-free model will have to increase gas abundances to get enough absorption, as we've seen already. You have to increase the greenhouse gas abundances. So this is I think this is the main plot. I've added a few extra things here. So this is the short wavelength versions and the long wavelength versions of the balances. These two plots are what they claim to be observational data, so real empirical data, and this is their real cloud model, and this is their cloud-free model, essentially. So again, short wavelength, long wavelength stuff. So again, they run millions of these simulations rather than a full climate model, so they can explore all the parameter spaces. C and D again are the cloud and no cloud models for net radiative forcings, and again, these are the observed climatology. And they claim in the end that emitting clouds means the global energy budget is not properly represented, and you can see that in several ways here, which I've talked about here a little bit. So for the outgoing shortwave radiation, it's 81 versus 106. So here it is with the cloud-free model, the outgoing radiation, and they actually see more like 106. So they say it doesn't match the shortwave radiation.
What's the upper right panel?
Upper right is empirical data. This is climatology data. That's what they say. Both of these are
So
from
there's two different estimates.
Yeah, two different estimates of the data. Elevated outgoing long wavelength flux, 261 versus 236. So they're comparing these, but it doesn't matter whichever one you compare. The outgoing flux doesn't match up. And depressing downward long wave flux at the surface, again, 320, which is here, versus 350, more or less, here. So they're saying that there's no way that a cloud-free model is going to match up even with what we see day from all of this stuff. Okay, then there's some more figures. I don't want to go through all these because it might get too boring, but comparing spectrally resolved energy budgets between cloud-free and real cloud models in shortwave and longwave. Everybody's seen some of that. Large differences in greenhouse effect and solar absorption. We saw that in this previous. Radiative forcing with increased CO2. They play around with that. They can be strongly overestimated in cloud-free model relative to a real cloud case, obviously. And then again, comparison of these spectrally resolved long wavelength forcings for larger amounts of CO2 in both of those cases. They show that in another figure. I think this is my last slide, basically, on this topic. But anyway, here they go through section 5. I asked Andy to read this more carefully since he came by and asked what actually should be the most important thing to read. I don't know if it is or not. But they go through in section 5 what the cloud fraction would have to be in different scenarios, water path, particle size, and cloud height. One of the arguments for having a lot of clouds is that there are more clouds found over the southern oceans on Earth, and they say if there are less continents, there's probably there are probably more clouds back then because there'd be more ocean coverage. Yes, well, I'm just telling you to say they show some plots about that. Can you comment on that?
Yes. So where the clouds over the southern oceans are more an issue of what the dynamics is than the fact that there's ocean there.
Right. Okay, good.
It's not to say that you can't get more clouds over the southern oceans if you have more ocean. It's just that it's not as simple as more ocean means more clouds.
It isn't, okay. Or maybe it's my primitive reading of what he wrote, but that's
Yeah,
what
that's what they said.
That's what they said. Okay, good. All right. Cloud water paths effects on short and long wave lineation depending on cloud height. So that's also very important. They play around with that quite a bit. Particle size, again, depending on, these cloud condensation nuclei. Again, I mentioned this before, how they're larger over ocean than land, according to what they said. What makes up the CCN now?
Larger droplets over.
Yeah, droplets, sorry.
Not larger CCN.
Yeah, I'm sorry, not
Fewer CCN.
Sorry for my what made up the CCN now versus then is very strongly debated, as we touched on earlier, because the biogenic products probably would be different back then than now. And again, as I said earlier, sulfur plays some role in these cloud condensation nuclei and how they form drops, I guess.
Now, but we have no idea what was going on then.
I'm saying we don't know, right? Exactly.
Well, there's still sea salt.
Sea salt. Was the salination of the oceans the same?
I've had less pressure in the past. It's been getting saltier time. Is that not true?
I think the whole chemistry is totally different, probably.
Yeah. And then no one really has a good idea of what exactly it is, because there are no proxies for salt.
No proxies for knowing what the salt distribution was back then. Again, possibly different concentration. So they say, if I get this right, fewer cloud condensation nuclei in general means larger drops that'll rain out quicker and the clouds will be less reflective. More of these nuclei around mean more drops that are smaller and more reflective. That's kind of a quick summary.
Cloud aerosol indirect effect.
Aerosol indirect effect. Andy, you think that's?
Yeah, that's conventional wisdom.
Okay.
But I still don't know why a reducing atmosphere wouldn't have biology to make lots of little particles. I don't quite understand that. Is there no, I mean, you can have biology in a reducing atmosphere, no?
The first geochemical traces that are assumed to be signs of life are 3.8 billion years old. What those organisms in the ocean would have been doing at that point in time is anyone's guess, but you can assume something, possibly.
And you could assume they make no particles, or you could assume they make particles.
That's the fun part of this time in Earth history.
You can do whatever you want. Okay, cloud height, I just mentioned that quickly. So larger forcings from raising the clouds, that won't surprise anybody here. Thicker, cover more of the sky initially, depending on the kind of cloud, of course. This goes back to these very high cirrus being very cold. Greater the radiated long wave effect at standard height, greater effect of
So what's
changing tide.
what's the physics for raising the clouds?
They don't.
They just assume that clouds.
Yeah, they just go in their model. They just play with it. They let the clouds
Yeah,
go up,
okay.
and they see what the forcings will be because they get colder. Of course, that does better trapping longer wavelength radiation.
Right.
Et cetera, et cetera.
Yeah. I think
But the mechanism, I don't think they.
The problem is that if you ask, why the high clouds are there in the first place in the current climate, because convection's pumping the water.
They do mention something about convection stuff in the paper, but I don't remember exactly what it was.
Oh, it was very good. They said without an ozone layer, there would be not much of a tropopause, and so maybe you wouldn't get these blow-off anvils, and maybe all the cirrus would just go very, very, very high, and there's no reason to think you would. It's kind of against Lindzen's idea.
Or without a hot surface.
That goes the other
Convection
way.
in the first place. Right,
So without a hot surface, what?
You're not gonna have convection in the first place.
You're not gonna have convection in the first place.
So,
Okay.
yeah, this is from the 3D model.
No, this is all
It was,
one column.
That's all from one column.
Yeah, they haven't done any 3D stuff.
It's interesting to see what the temperature profile is.
I don't think they have. Did they have a temperature profile?
I don't have that. This.
And what? Well, let's see. And then
I
the
think
last.
they treat their clouds largely as
Just
an
as an
independent
external-
thing, then they run like 16 million
Yeah.
kind of variations on their 7
Yeah.
parameters.
Yes, 16 million grade. Lots of nice plots in this paper. But yeah, I don't think there's any temperature profile in here. Just cloud fractions and.
No, the tropopause thing came up when they were in there shredding Lindzen, basically.
I thought this one of these last statements was interesting. Pressure of the arcane was likely not 1 bar, so no oxygen and nitrogen inventory was different. So the oxygen and nitrogen inventory was different. This would change the lapse rate and tropopause pressure, hence the type of clouds. So again, they don't know, I guess, what kind of clouds is what they're saying here, if I understand it correctly.
It's complicated.
It's complicated. It's a relationship.
So what's the bottom line? That, you can overcome the paradox with clouds, or you in a variety
I
of
think
ways?
that these
or
people
you
are
can't?
saying that you have got to use clouds to overcome
Because
them. If
the
you're going
algorithm-
to overcome this paradox, you have got to use clouds. You cannot have a cloud-free model.
But that
Make it
everyone else who
work.
has done it with clouds has done it wrong.
Yes.
So they don't have the answer, they just know that everyone else is wrong.
And they don't believe the organic haze?
They don't touch on the organic haze.
So that's a cloud-free solution, potentially.
The organic haze is a cloud-free. I don't think Wolf and Toon really talk about clouds again, which is a pity that they don't. I mean, I imagine Brian knows something about clouds.
Well, yeah, when we had this result of clouds dissipating when you run out of particles. He said, "Oh, we should write a paper to solve the faint young sun paradox," but we never did write that paper.
So just to,
Yeah.
is that the last?
That's it.
So there's one other sort of potential astrophysical complication here. Well, I say astrophysical, I guess it's planetary science, but so my understanding, looking at recent literature, is for a long time the received wisdom about the early Earth was that somewhere between about 4.1 billion years ago and 3.8 billion years ago was this late heavy bombardment. So there were dynamical rearrangements in the outer parts of the solar system that ended up sending a lot of life-killing size asteroids inwards on Earth-crossing orbits, and there's good evidence from lunar impacts and so on that this was going on. It was intense bombardment of the young Earth up to around 3.8 billion years, and that's been the received wisdom. But now it seems, and maybe you know more about this, that people are saying that actually in the rock record there is a lot of evidence of little spherules from big asteroid impacts stretching all the way to say 2.5 billion years ago. Not at a rate. Previously, the idea was it tailed off pretty quickly around 3.8 billion years ago, and so maybe then every few 100 million years you'd get one of these really big impacts. The new picture is that it was happening every 50 million years.
How do they square that with the moon? Because, the lunar record is unambiguous.
Well, you can
Yeah,
answer that.
I mean, you can still have quite reputable people argue about this, about whether the samples brought back are really addressing whether there's a universal feature at 3.8 billion years ago. It sort of boils down to the fact that just about everything was caught up with Mare Imbrium, which was 3.8 billion years ago.
And my understanding is that the geological evidence here is looking pretty good. That there are many episodes of big impact.
But I mean, is that geological, does that evidence represent many places on the Earth? Because you're saying object to the moon, you know, how much stuff do we have on the Earth that's that old?
Not all that.
That's my concern about all
Right.
the geological arguments that they might be looking
Yeah,
at something
sure. You know,
atypical.
not my expertise, but what I was interested in with that is, and I've forgotten the name of the people who wrote about this recently. I think it was
in Science, wasn't it?
Was it in Science, or was it just reported at a meeting?
I read it somewhere.
Anyway, some people have pointed out, if that were the case, if there was this continued, pretty regular impact, then you would be dumping things like sulfur compounds into the atmosphere on a pretty regular basis, and that would make the faint young sun problem even worse, right? And I thought that was interesting, because then, because reading these papers, I feel like, yeah, okay, maybe there isn't a single, beautiful phenomena that takes care of it all. It's all to do with clouds and understanding the subtleties of this. But then if you add in another detrimental effect, then you really come back to looking for some big solution that's going to completely fix it. At least that was my take on it.
So now we're going to start reading papers that compensate for the sulfur through some other mechanism.
Right.
Okay. Yes, please.
Can I ask, what's the functional difference between what they're calling clouds and what Wolf and Toon are calling haze?
The haze is above everything else, basically,
Okay.
if I understand correctly. It's this very thin, kind of like,
Well,
So
the
it's-
cloud
It's
physics have
stratus-
a thermodynamic difference, which is cloud particles, once they start growing, will continue to grow if they're in supersaturated region, where a haze is stable, and so it stays at a small size.
So like our stratospheric sulfuric acid haze today.
It's very small, hangs around for a long time, whereas clouds seem to be constantly generating new ones, and this
And
little
the,
stuff
and
falls
the
out.
hazes are usually photochemical products.
Mhm.
Suppose something would be sensitive to how much water you're evaporating from the ocean. And smaller particles too. I mean, that's gotta be an important part. Somehow that's gotta be tied into why, was it Wolf and Toon get the answer they do, is somehow they must be making haze particles that are a lot smaller than the ones that are really tight, right? Because the
Well, the
scattering
aggregates are smaller and
scattering
there's-
optical thickness.
But they said the scattering is the same.
They get an optical thickness of about 1, they say.
Right.
And
okay.
when they say they get the same optical properties, they just cite some Tomasco, whoever came up
Marty
with.
Tomasco.
Yeah, he came up with this, and then they used it. So it's a little slippery.
Yeah.
So if they're a tenth of a micron, then you can get optical depth of 1 in the visible and optical depth of 3 by the time you get to the UV.
Yeah.
So maybe the aggregates are not the same size at all.
Right. Whereas the Titan hazes must have, I can't give you a number for what people say about them, but they must be larger because they still have substantial optical thickness in the visible, and they don't become semi-transparent until you get into the near IR.
Basically, they have their monomers, right? So the fractals are all these little things. They're picking the size based on Titan.
Okay, so then maybe it's then.
So I think it's a big.
It's just purely then an amount, I guess.
I had one more comment. This was just, I chanced across a paper which I thought was kind of interesting, and I suspect it may be completely wrong. This is, the author was Bada and a couple of others. This back from
Bada, you mean the original Bada?
I think it's possible. This was in the 1980s or early 90s, perhaps.
He wasn't around.
Okay, someone else then. And actually, Chris Chiber in his paper refers to this at the very end of his discussion. And so it's kind of a devil's advocate idea, is that the assumption here is that the Earth had to be sort of melted through, right? That you had open ocean everywhere. So they ask, well, what if in fact you really did, you start with a snowball Earth, but the ice layer is not that thick, maybe it's 300 meters thick globally or something like that. And geothermal energy keeps everything liquid underneath, so you have a huge liquid ocean. It's sealed off,
Yeah,
it's
that
capped.
was referred to in one of the papers. They referred to that someone had proposed that as a solution,
Right,
a
and
Europa-type solution.
I think that was the Chiba paper. So, what I just don't know whether that is seen to be, in terms of the geology, the geochemistry at all feasible anymore, whether that was just a wild idea. What was kind of fun about it was that they claimed that, okay, so how do you then thaw out in time to do all the things you want to do in around 2.5 billion years? And they actually claimed that if you're pelting the Earth with asteroids that constantly break this ice sheet in really big areas, continental size areas, then you can have gas cycling and you can actually encourage prebiotic chemistry, and eventually you break the eggshell and enough greenhouse gases pump out to flip the system to a warmer.
How frequent is this? I mean, what area is
they were very vague about this, right? This was very much
that would be amazing.
This was one of these
How big
wild
of
ass
an impact do you
ideas
need to break through 300 meters of solid ice?
100-kilometer asteroid will
Yes.
go through it.
So one of these 100-kilometer asteroids comes in
No,
every
they're talking about big
few months.
impacts, right? And, but I guess what I thought was interesting was, it talks about, well, I mean, all of this worries about the why wasn't, what do you have to do to make, liquid water oceans on the planet? Well, does it matter if they're capped with ice or not? That I don't understand. Because if they can be capped with ice, then you can relax a lot of the requirements here.
But Linda, what do you think about that? I thought there's a lot of evidence that it was liquid.
Well, it's still liquid, right? It's just
no, but I mean,
underneath.
So make sedimentary rocks, right?
So yeah, well, when you get back before 3.8 billion, when most of what you have to look at are basically fluid inclusions in zircon crystals, so very, very small representation of whatever environment those crystals formed in. The oxygen isotopes have suggested temperatures that are pretty comfy, not cold. And assuming that these are volcanically produced zircons, that would say something about the general temperature of the atmosphere. So that would be, for the few zircons that do exist, there would be an argument for at least not having a constant cold state with a frozen over ocean.
A really dumb question, right?
Sure.
I mean, can you make zircons and do all of this in the deep ocean somewhere? Does it have to be something that has access to the atmosphere?
The general wisdom is that the zircons crystallize so fast when you have the material ejection to the atmosphere that's really sort of more of an instantaneous capture. I'm not sure that people have actually tried to suss out whether or not they are.
So these guys, maybe that's another name for they're talking about oxygen isotopes of cherts, and they're saying 70 Celsius is the water temperature.
Chert's different. Chert is microcrystalline silica.
But anyway, it's 70. It's hard to believe it's going to be 70 Celsius beneath global ice.
Right, sure, yeah.
I find 70 Celsius somewhat uncomfortable for
Who do they reference when they mention that?
Bacterium.
Because if it's who I think it is.
2021.
If this is Paul Knopf, it's old
Well, maybe it depends on where
material.
where you're from. Maybe the equator is hot.
We're only criteria to stay under 100.
Stay under 100. Yes, that's right. Don't want your waste oceans boiling off.
Yeah, Paul Knopf. There's a guy who works a lot on our PNH cherts, and he has come up with these estimates, and he doesn't convince a lot of people.
So the 70 is probably an upper limit.
Let's hope
Well, I think the 70 isn't that based on oxygen isotopes?
It's based on oxygen isotopes, and
So hard to calibrate going back then.
well, the trouble is that you can get diagenetic changes,
Right.
altering what you
Your baseline or
yeah, and so I think part of the issue that people have had really with the stuff that he's looked at is basically he's not been able to control for potential diagenetic effects on these isotope signatures. So yeah, because if it's a burial signature, then sure, why not 70 degrees C?
So it seems like 3.8 million years ago, I think that's, that you mentioned earlier, I mean, there are like sedimentary rocks in Greenland. It seems like those, you would actually need some like continental weathering cycles.
Well, they are actually metamorphic rocks, but the composition of the rocks suggests that they were originally sedimentary, and that's how they get to the idea of having to have a water cycle with erosion and so
Right.
on. Yeah. Most of the other bits and pieces that are older than that are really just down to a few crystals here and there that are reworked into younger rocks.
Talked about Mars.
We haven't talked about Mars. Yeah. We can do that next time. Well, I was gonna ask, what about these banded iron formations? The whole basis for this saying there's not too much CO2 in the early atmosphere. Do you think that's also reliable data? These measurements of siderite, I guess, and then they mentioned, what is it, magnetite and fulgurite, all these other iron species which are
Well, yeah,
ghost
the
ions.
idea is that if you have this much iron in solution in the oceans, if you had any oxygen at all, the oxygen would be combined to the
I'll
iron.
have the equal pepper.
So the fact that you don't see this happening before the late failure from
But wait, I thought the argument was there's no CO2. It didn't have lots and lots and lots of CO2.
So they propose an atmospheric concentration 100
I don't think I
times
can do this.
required to form siderite in banded iron formations.
Well,
But they don't find that. So why do they think that, I wonder? Oh, maybe the CO2's, maybe it's disassociated and the
Well-
O2, or maybe it's,
Well, siderite's is an iron carbonate, and so, you know, I don't know the chemistry specifics for this argument all that well, but there are not a lot of carbonate rocks, period, going that far back, and so I don't know that just, you know, the siderite issue is
it's conclusive.
conclusive.
So you don't think the CO2 argument is that solid? So maybe we could have concentrations of CO2 much higher? Because a lot of these people are quoting this kind of data, these banded iron
Yeah.
formations, they call them, and they all, I mean, none of these people are geologists, but they all seem convinced by it. I wish we had a geologist here.
Yeah.
But none of the papers that I read anywhere where anybody said that there was any evidence of much higher CO2 concentrations based on any other lines of evidence. So maybe there just is no other way to get any other lines of evidence. What do you?
I think it's not as solid an argument perhaps as some might suggest.
So maybe it's possible there was higher concentrations of CO2. That solves a lot of the problems without invoking photochemical hazes that may or may not exist in things. Or cloud type, even cloud could be similar.
By the way, I just reread the Zami. What Zami says is you can't solve it by getting rid of the low clouds. To do it with high clouds, it's crazy.
Yeah, he does.
But you can't ignore clouds. That's what they say.
Yes.
But they have no solution.
No. But he says using these high thin series only is not a good solution. Okay, well, thank you all for coming.
great.
30% less. So
I can think of the house no longer, you know, like being built out by acid impact, like.
Thanks for coming, Arlen.
You know,